Hey, so hello and welcome. So today we are going to discuss the relativistic dynamics. So until now we have learned about the relativistic principles, the concepts of four vectors, the metric tensor, the Minkowski metric tensors, tensor eta ij, and the tensorial description of the relativity. So until now what we have done is the tensorial description of relativity, of the special theory of relativity. But what we have not done is to define, we have not done until now is not done, is we haven't defined the momentum. How do we define momentum? And energy as well as the angular momentum. So all these quantities are very familiar to us from the classical mechanics, but did not we didn't see them whether in relativity how do they change, whether they change or not. So we have to see. So, in order to proceed further into the dynamics, we need to define and understand these properties from the very depth. So that is what is the aim here. So to do that, the what we are going to do is, our approach will be to calculate everything from the Lagrangian. Okay. So from classical mechanics, or rather, this is also classical mechanics, but I will say from non-relativistic mechanics, we know that, let us consider for the simplicity that there is only one particle. So the Lagrangian is a function of generalized coordinate q, the generalized velocity, and the time. If the Lagrangian is such that, then we know that the conjugate momenta is equals to del L over del Q dot. So we can use this thing to find out our momentum, and then we can do something like a kind of legendary transformation of Lagrangian, something like PQ dot minus L, which we do in the non-relativistic mechanics, and then we can find this as energy function. So once we find momenta using this equation, we can put that here, and then we can find energy. So that is going to be our game plan here also. But the point is, we do not really know what the Lagrangian is. So first we have to form the Lagrangian to achieve our goals. So that's why we have to do relativistic Lagrangian. So let us give a little bit thought what our relativistic Lagrangian could be. One thing is for sure that the since the relativity principle demands that the laws of motion or the equation of motion, so either we call laws of motion or equation of motion should not should be same. Otherwise, should say should be same in all inertial frames. In all inertial frames. So if you remember when I introduced the relativity to you, so this was the second, sorry, this was the first axiom of the relativity principle. This was the first axiom, and the second axiom was the constant speed of light, right? Constant speed of light. So that was our introduction to the concept of relativity. So we are from, the new Lagrangian has to respect the relativistic Lagrangian which we want to form has to respect these two principles, right? So if so, basically, what the first equation, the first statement says is that our Lagrangian R, so R here means relativity, special relativity. So Lagrangian in the relativistic case should be an or not rather a Lorentz invariant quantity, because Lorentz invariant quantities are those which do not depend, which are invariant under Lorentz transformation, or which are the same in all the inertial frames, right? So what are the what is the most basic invariant quantity that we have in the relativity? So it was our ds square. or ds, right? So it was ds square, or we can call ds. So ds, which was equal to eta ij dxi dxj under root. This was our Lorentz, the most basic Lorentz invariant quantity, and it is, like, you can say that it is a geometrical quantity. It is how the very much geometrical nature of space time is, right? So we can choose this quantity to be our relativistic Lagrangian. So that is the motivation here. So this Lagrangian automatically respects the relativistic principle, right? So what we can do, we can simply say that our Lagrangian would be integral alpha. So we have to set alpha. I'll tell you, we'll be setting up this alpha so that our relativistic Lagrangian should look like this, right? And this ds would be from, let's say, like, we have some event from a to b, something like this. So we are integrating over from a until b. So this should be our relativistic Lagrangian, right? Okay, so now we already know the form for a particular form for ds. We know what ds exactly is in relativity. So let us just do that. So ds square, let us write ds square first. So it would be something like, it was my c dt square minus dx square minus dy square and minus dz square. This was our ds. And now when you take under root, it would be everything inside the under root. So if we write the relativistic Lagrangian, it would be alpha and under root c dt square minus dx square minus dy square minus dz square. Okay, cool. Now what else do we know from here? So instead of writing this one, we can simply take out the dt from here, right? We can take out the dt term here so that the integration will be in terms of dt. So what we can do is, or rather, we can take out the c dt completely, and should be c square. So it would be 1 minus, and then when we take out the dt, it will be dx by dt, dy by dt, and dz by dt square, and added up all the components, which is just the velocity vector magnitude square. So I will write it like this, and this will be c dt, right? But dt here, and also this is, let us just call it this u instead of v. Let's call it u, because that's how we have used the notation earlier as well. So it would be 1 minus u square by c square c dt, right? But now what we want to do is, we want to eliminate the dt here, or rather, like, we can imagine this to writing this thing in terms of our proper time as well. So what was proper time? So proper time was c square d tau square is equal to same thing ds square. So what I was saying is that we can also write in the very compact form. We can write it as something like c d tau, right? So either you write this thing here, or you write this one like this. It's same, right? And then from here also, you can see that if you plug in the expression for c d tau, it would correspond to this thing only, which is there, right? Okay, so now we proceed from this equation here, relativistic Lagrangian, this equation. Now we do not know what alpha exactly here is. So we have to set up alpha. So we have to calculate alpha. So as we know that under the limit, to calculate alpha, we see that under the limit v by c tending to 0 is like v, which means that our velocities are much smaller than the speed of light, then our under this limit, then our Lagrangian for the relativistic Lagrangian should tend to non-relativistic Lagrangian. And we know for a non what is the non-relativistic Lagrangian. So by the way, when I write this relativistic Lagrangian here, it is just for a free particle. So this Lagrangian is for a free particle because the very much reason is that it only considers the space-time interval. It doesn't have any other interaction. So we are not taking into the account any interaction. So when we take interaction, there will be different terms from this, right? So right now we are doing only free particle so that we can set up this alpha, right? We can calculate the alpha. So from here, if we plug in the limit for here, if we if we plug u by c to be 0, then we should get something, then we should get relativistic Lagrangian to be something like half m u square, isn't it? Because free, a non-relativistic Lagrangian and free particle Fp, it is simply kinetic energy, which is just this thing, right? Okay, so from here, from the above equation, we see that our Lagrangian, or rather, one mistake that I've made all this time is that I've just used this thing as relativistic Lagrangian. I'm so sorry. It is action, relativistic action, and not Lagrangian actually. So I have to do action everywhere. Lagrangian is what is inside the integral, right? So from here we basically, so actually this equation is also wrong. Let me write here what the relativistic Lagrangian exactly is. So the relativistic Lagrangian is what is inside the integral. So it is just alpha 1 minus u square by c square, and c is also there. So this is my relativistic Lagrangian, which should tend to the non-relativistic case under the assumption of u by c tending to 0, right? Okay, so now under that limit, my relativistic Lagrangian would be, let us rewrite it, uh, it would be alpha c and 1 minus u square by c square to the power 1 by 2, right? So what we can do, we can write this thing in binomial expansion, 1 minus u square by c square 2, right? And just neglect the rest of the terms. So here we have something alpha c minus alpha c by 2 c square and u square. But this thing is just a constant, right? It is a constant. So anything added to the Lagrangian or subtracted, it doesn't matter. Constants adding subtraction doesn't matter because it doesn't affect the equation of motions, because equation of motions are in terms of derivatives, right? So we can finally write a relativistic Lagrangian as minus alpha c by 2 c square u square itself. Now it is very easy to see that if we compare, it should be half m u square, and in here it is minus 1 by half, 1 by 2 alpha by c and u square. So now you can identify that alpha should be equal to minus mc. Thus, we have calculated alpha. Now we can write our relativistic Lagrangian in full generality, and that would be from where? From this equation. So just plug in alpha is minus mc. So we will get minus mc square under root 1 minus c square by c square. This is our relativistic Lagrangian. Just comparing, just comparing the relativistic and non-relativistic Lagrangian for the free particle. So let us write the non-relativistic Lagrangian for the free particle. We have half mu square. What is the very basic difference that you see in here? So if you look closely, if I put, let's say, u is equal to u vector is just equal to 0, if we put that, right? So Lagrangian, relativistic Lagrangian tells you that it would be minus mc square, but non-relativistic Lagrangian is equal to 0. And notice that the Lagrangians have the units of energy. So it is kind of giving you hint that when the velocity, even when the velocities goes to 0, there is some energy inside the system, right? And that order is mc square, which is very famous equation. E is equal to mc square. Everybody uh, grows up hearing that. And in the non-relativistic case, it's just zero. If a particle is moving, it makes sense that in non-relativistic dynamics, we see, yeah, there is no kinetic energy, there is no potential energy, where there should be energy. But then there is a concept of rest mass energy, which we will see in full generality in the relativistic dynamics. So the next step is to find momentum and energy out from this relativistic Lagrangian. Okay.